In science, few things are more unsettling than when the universe refuses to follow its own rules, when the numbers don't add up, when the instrument reads something that every theory says it shouldn't be reading, when nature, as one physicist famously put it, simply hasn't read the textbook. In 2012, Voyager 1 crossed into interstellar space, and its magnetometer sent back a reading that stopped scientists cold. The magnetic field outside our solar system was pointing in exactly the wrong direction. Not slightly wrong. Not off by a few degrees within measurement error. Off by more than 40 degrees, in a way that decades of theoretical models had categorically said could not happen. And then, 6 years later, Voyager 2 crossed into interstellar space on the other side of the heliosphere, in a different location, at a different point in the solar cycle, and its magnetometer read essentially the same thing. The anomaly wasn't a fluke, it wasn't instrument error, it was real. And it was forcing scientists to confront the possibility that our most fundamental model of how our sun interacts with the galaxy is wrong in ways we still don't fully understand. Today, we're going to break down exactly what Voyager 1 detected, why it terrified theorists, what it took to begin explaining it, and what it might mean for our understanding of the invisible forces that shape the space around our solar system. To understand why this discovery was so alarming, you first need to understand what scientists expected to find. Our sun is constantly blasting charged particles outward in all directions. The solar wind. This wind carves out a vast bubble in the surrounding interstellar medium, the heliosphere. Inside the heliosphere, the magnetic field is dominated by the sun. It spirals outward from the sun in a pattern, called the Parker spiral, named after astrophysicist Eugene Parker, who predicted its shape in the 1950s. That field has a very specific orientation. Everyone knows what direction it points in. The solar magnetic field has been measured directly, continuously, for decades. Outside the heliosphere, the field is different. Interstellar space has its own magnetic field, a weaker, more ancient structure generated not by our sun, but by the collective magnetic history of nearby stars and the gas clouds between them. Astronomers had measured this galactic field indirectly for decades, using other spacecraft and radio telescope observations. They knew roughly what direction it should point. And the prediction was straightforward. When Voyager 1 crossed the heliopause, the boundary where the sun's wind meets the interstellar medium, the magnetic field direction should flip. It should shift from the solar orientation to the galactic orientation. A clear, measurable change. The theoretical models all agreed on this. It was considered one of the definitive signatures that would confirm a spacecraft had truly entered interstellar space. In fact, when the Voyager team was debating in 2012 whether Voyager 1 had actually crossed the heliopause, the magnetic field direction was listed as the single most critical test. Voyager project scientist Edward Stone said it plainly. The last critical indicator that Voyager 1 had reached interstellar space would be a change in the direction of the magnetic field. That was the threshold. That was the definitive proof everyone was waiting for. Cross the boundary. Field changes direction. Simple. Clean. Predicted. And then Voyager 1 crossed, and the field didn't change. On August 25, 2012, Voyager 1's instruments registered a sharp, unmistakable boundary. Solar particles plummeted. Cosmic rays surged. Every other indicator screamed that the spacecraft had crossed into a fundamentally new region of space. But the magnetometer, the instrument measuring the direction of the magnetic field, barely moved. The magnetic field strength jumped by about 60% at the boundary, confirming that something had changed. But the direction, it changed by less than 2 degrees. For context, the predicted change was on the order of tens of degrees. The field outside looked almost exactly like the field inside, as if the heliosphere's magnetic fingerprint had somehow bled right through the boundary into interstellar space. Stamatios Krimiges of Johns Hopkins University Applied Physics Laboratory, one of the senior scientists on the Voyager mission, described the reaction with characteristic scientific candor. It just so happens that nature hasn't read the theorists' papers and didn't know that it was supposed to change the magnetic field direction. That quote became something of a famous line in astrophysics circles. It captures, with unusual honesty, the disorientation the scientific community felt. Every model said the field should change. The field did not change. Something was wrong, and nobody was sure what. For months after Voyager 1's crossing, the debate was fierce. Some scientists argued that the unchanged magnetic field meant Voyager had not actually crossed the heliopause, that it had entered some intermediate region, perhaps a previously unknown zone between the heliosphere and true interstellar space, which some researchers called the heliocliffe. Others argued that Voyager 1 had definitely crossed, based on all the other data, and that the magnetic field anomaly was simply a challenge to existing theory that needed to be resolved. It took more than a year, and an unexpected gift from the sun itself, to settle the question of whether Voyager 1 had truly entered interstellar space. But the magnetic field mystery remained open long after that. 6 years later, on November 5, 2018, Voyager 2 crossed the heliopause from the other side of the heliosphere. Same story. Different location, different time in the solar cycle, different conditions, and the magnetic field again refused to change direction in the way theory predicted. Bernard Berlanga, the NASA Goddard scientist who led the magnetic field study for Voyager 2, said it directly. The field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. With Voyager 1, scientists had only one sample, and they could argue it was a coincidence or a local quirk. Voyager 2's matching result closed that argument. This was real. This was systematic. And that meant the theories were wrong. Or at least, profoundly incomplete. Here is the key question the data raised. If the interstellar magnetic field is supposed to point in one direction, and the solar field points in another, why do they align at the boundary? What force is strong enough to bend the galactic magnetic field so that it runs parallel to the Sun's field right at the edge of the heliosphere? And why does that alignment persist not just at the boundary, but for a significant distance beyond it? These questions don't have fully satisfying answers yet. But the best current explanation involves a process that is, in its own way, as remarkable as the anomaly itself. A team led by astrophysicist Nathan Schwadron, at the University of New Hampshire, published a study in the astrophysical journal Letters, proposing a resolution. Using data from multiple spacecraft, including the Interstellar Boundary Explorer, NASA's IBEX mission, they argued that Voyager 1 is not yet in truly pristine interstellar space. Even beyond the heliopause, the Sun's magnetic influence is still distorting the surrounding field. Think of it like the wake of a ship. The ship has passed, but the water behind it is still churned and distorted long after the hull has moved on. The Sun's heliosphere is plowing through the interstellar medium, and behind and around it, the galactic magnetic field is being draped, compressed, and rotated away from its natural direction. Schwadron's team showed that the interstellar field around Voyager is being deflected like an elastic cord wrapped around a beach ball, bent to conform to the heliosphere's surface, rather than pointing freely in its natural galactic direction. But the direction anomaly is only half the story. There is a second magnetic discovery from Voyager's data that carries even bigger implications, and it concerns not the direction of the field, but its strength. Before the Voyager crossings, scientists had modeled the interstellar magnetic field's strength and arrived at an expected value. Voyager 1 measured it directly. The result: the interstellar magnetic field was approximately twice as strong as predicted, around 5 microgauss, compared to the roughly 2.5 microgauss that models had calculated. And when Voyager 2 crossed in 2018, its measurements showed the field was even stronger on that side, around 7 microgauss. Both readings dramatically exceeded what the theoretical models expected to find. This matters enormously, not as an abstract number, but because of what a stronger interstellar magnetic field does to our solar system. The interstellar field presses against the outside of the heliosphere constantly. The heliosphere expands outward due to solar wind pressure. The interstellar medium pushes back. The balance between those two forces determines the size and shape of our protective bubble. And a stronger than expected interstellar field means the field is pressing harder against the heliosphere than we thought. Much harder. The pressure from a magnetic field scales with the square of its strength, so a field twice as strong doesn't exert twice the pressure. It exerts 4 times the pressure. A field 3 times as strong would exert 9 times the pressure. The numbers compound rapidly. Kremigis described the effect vividly. The strong interstellar field acts like a straitjacket around the heliosphere, suppressing most of its expansion and contraction. This is why both Voyager spacecraft crossed the heliopause at nearly the same distance from the Sun, about 120 astronomical units, even though they crossed at different points in the solar cycle, when the solar wind strength was very different. Normally, a stronger solar wind should push the boundary further out. A weaker wind should let it contract inward, but the two crossings happened at nearly the same distance. The reason, in Kremigis's interpretation, is that the unusually powerful interstellar magnetic field is holding the heliosphere rigid, preventing it from expanding and contracting as freely as theory predicted. Our protective bubble is being squeezed from outside by a force twice as powerful as we accounted for. And then, in 2020, things got stranger still. Voyager 1's magnetometer registered a sudden, sharp jump in the intensity of the magnetic fields embedded in the surrounding interstellar plasma, and simultaneously, the plasma density also spiked. Previous spikes like this had occurred before, and scientists had traced them back to pressure waves from the Sun. Solar eruptions that sent ripples propagating outward through interstellar space. Those previous spikes had lasted months, then faded. The 2020 anomaly was different. It didn't fade. Months passed. A year passed. The elevated magnetic field intensity and plasma density persisted, and kept persisting after Voyager's 2023 communications blackout was resolved and data began flowing again in 2024. Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and the principal investigator for Voyager 1's magnetometer, proposed a striking explanation. He suggested that the persistent anomaly could indicate that Voyager 1 has entered a small cloud of ancient interstellar plasma, material ejected long ago by a nearby star or star-forming region, carrying the magnetic field signature of its origin. Not our Sun's magnetic fingerprint, not a solar pressure wave, but the magnetic remnant of a completely different star's history, drifting through the interstellar medium, and Voyager 1 has flown into it. If that theory is correct, Voyager 1 isn't just in interstellar space, it is inside the ancient debris of another star. That is not a small claim. Szabo is careful to note that this is one theory among several. Other scientists believe the sustained anomaly is still a solar origin pressure wave, just an unusually large one, of unprecedented size. Still others argue it suggests Voyager 1 hasn't fully exited the heliosphere's outer influence yet. The honest scientific answer is, we don't know. Stella Acker, a researcher at Caltech studying Voyager's plasma wave data, noted that it is surprisingly difficult to observe the interstellar medium right outside our own heliosphere, the region where Voyager is operating. We're good at studying things far away, we're good at studying things inside our solar system, but the transitional zone just beyond our cosmic doorstep, that's exactly where our models break down, and exactly where Voyager 1 is our only instrument. Let's bring all of this together. Voyager 1 detected a magnetic field outside the heliosphere that refused to change direction, challenging decades of theoretical models. Voyager 2 confirmed the anomaly from the other side of the solar system, eliminating coincidence as an explanation. The interstellar magnetic field was found to be approximately twice as strong as predicted, strong enough to act as a permanent external constraint on the size and shape of our heliosphere. And since 2020, an unexplained sustained spike in magnetic field intensity has raised the possibility that Voyager 1 may have drifted into an ancient stellar cloud carrying its own magnetic history. Every single one of these findings was unexpected. None of them appeared in the models that were considered state-of-the-art before the crossings happened. What does it mean for us, for Earth, for life on this planet? In the short term, nothing immediate. The heliosphere still protects us. Our planet is still shielded from the most energetic cosmic rays. But on longer timescales, hundreds of thousands to millions of years, the strength and behavior of the interstellar magnetic field matters a great deal. A stronger interstellar field means a more compressed heliosphere. And scientists now have evidence suggesting that around 3 million years ago, during a period when the solar system may have drifted through a denser region of the interstellar medium, the heliosphere shrank so dramatically that Earth was briefly exposed to raw interstellar space, with potential consequences for climate, atmospheric chemistry, and possibly even human evolution. The interstellar magnetic field isn't just an abstract quantity. It is one of the forces that has helped shape the conditions for life on Earth. The magnetic void that Voyager 1 detected isn't a void in the sense of emptiness, it's a void in our understanding, a gap between what we predicted and what we found. And filling that gap is going to require a new generation of spacecraft, new theoretical models, and probably a few more surprises along the way. If this kind of deep space science is what you come here for, mindless, subscribe, and hit the bell. Next episode, we're going to talk about what happens when Voyager 1 finally falls silent, what we stand to lose, and whether there's any chance of a mission to replace it. I'll see you there.